So in this video, I'm going to be going through how to derive the least squares regression line. Now, because there are two of them, you've got y on x and x on y, I'm only going to be doing one of them. I'm going to be doing the y on x line. The x on y one would follow a very similar calculation. Okay? Now, this is an extension video, so you won't have to replicate this in the exam. This is here for interest's sake. There will be I'll have to do a little bit of a crash course into some of the concepts initially, because I've got to explain what a residual is. But we will be looking at residuals later on in the playlist as well. Okay, so first of all, what do we mean by a residual? So let's say that this is your regression line, okay? Let's give it an equation. So I'm going to call it y hat. Okay, so I'm just going to put a hat on it. That's just a label. It doesn't mean anything special. And it's going to have the equation a plus bx. Okay? And then you've got one of your data points. Let's pop it there. Okay? And let's refer to this as a general data point. So it could be x1, y1, for example. But I'm just going to write that as xi, yi. Okay, so where I could be 1, 2, 3, 4, whatever data point you're looking at. Now, a residual, we use the Greek letter epsilon. Okay, so epsilon I, so the ith epsilon. Okay, so you would have an epsilon for each of your data points. Okay, so your residual is equal to your y value for your data point, okay, so the data point that you have collected, take away the y value that is predicted. Now the predicted y value is from here, so that would be your y hat, essentially. Okay, so that would be your residual. And what that does is, because it's above the line, that wasn't a particularly straight line, was it? Because it's above the line, it would actually give you that distance there, okay? But because what we've got to do is we've got to look at minimizing all of the residuals. The problem is that some of them will be positive, some will be negative. The ones above the regression line will be positive, the ones below the regression line will be negative. And there is a problem that they all cancel one another out if I just add them all together. So, to avoid that, I'm going to have to square them. Okay? So, first of all, let's remove the the y hat, and I'm just going to replace it with a plus bx. Now, the x coordinate is xi, so I'm going to have that there. Okay? So, that is the predicted y value. A plus bxi. Now I want to minimize the sum of all of the epsilon squared. So I'm going to refer to that as capital S, and it is the sum from I equals 1 to n of all of the epsilons added together squared. Okay, so, the sum from I equals 1 to n of epsilon I squared. So that would be epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared, etc. All the way up to epsilon n squared, if you've got n data points. So, essentially, S is equal to the sum. Now, I'll forego the I equals 1 to n here, okay, because we know what those bits are. It's just going to get really messy if I write all of those down all the time. So I'll forego writing I equals 1 to n now, because that won't change. So it's going to be the sum of all of that squared. So yi take away a plus bxi squared, like that. Okay? Right, so I want to minimize this. Now, this is essentially, because it's a minimization problem, it's an optimization problem. Okay, so essentially what I want to do is I want to differentiate this. But the question becomes, okay, well, if I want to differentiate it, in which variable am I differentiating it by? What am I trying to do here? Well, I am trying to find the value of A and B that will minimize S. Okay, so I'm trying to find the value of A and B that will minimize S. Now, because I'm looking at two variables here, so two variables A and B, and I want to get them in terms of X's and Y's, okay, essentially I'm going to need to differentiate with respect to A and differentiate with respect to B. Now, you could write that as ds by dA and ds by dB, and do it that way. But you might want to kind of like introduce here the idea of a partial derivative. Now, partial derivatives you won't have met previously, but essentially what a partial derivative is and how it's written is, where do I want to write this? Let's write it up here. So it's written like this. So this would be the partial derivative of S with respect to A. So when you get into multivariable calculus, rather than just differentiating with respect to X, you might differentiate with respect to X and Y if you've got something like a Z equals something to do with X's and Y's, and you're looking at 3D surfaces. So when you're looking at three-dimensional surfaces, you are essentially having to think about in which way you're going to cut it. Okay, so when you're talking about the gradient of a three-dimensional surface, okay, are you going to look at it this way, okay, along the x-axis, or are you going to look at it this way along the y-axis? Okay, so, and you could get different gradients depending, and different gradient functions depending on which direction you're looking at. So that's what partial derivatives are all about. You're looking at differentiating with respect to different directions in a 3D surface. So we use this symbol here to represent a partial derivative rather than using D. Okay, but for the purposes of this, if you just want to have ds by dA and ds by dB, it's not really going to hurt you at this point. Okay, but it's a little bit of kind of extension there for you to sort of like see like what's going on behind the scenes of some degree level mathematics. So I want to differentiate this with respect to A. Now don't worry about that summation symbol, okay? Think about differentiating this. Now you could expand the brackets out, but I'm going to use the chain rule differentiation to do that. Now the chain rule for differentiation is a second year A-level maths technique, or full A-level maths differentiation technique. It's quite straightforward to pick up at this point. Essentially, I'm treating A as the variable here, okay? So I'm going to have the sum. The derivative of the inside comes outside. So the derivative of the inside, remember, A is the variable, nothing else is. So we have this as a constant. The minus bxi is also a constant. So the only variable is the minus a, and minus a differentiated with respect to a is just minus 1. So minus 1 is going to come outside, and the 2 comes down to the front as well. So we're going to get minus 1 times 2, so minus 2, and we've got the yi take away a plus bxi, like so. And we drop 1 from the power. So that is me differentiating using the chain rule. So it allows me to differentiate it quickly. If you want to expand this out and differentiate each term individually, you can do that as well. And it's not going to be too bad because it's only squared. Okay? Right, so what I'm next going to do is I am going to, essentially I'm going to expand this out into several summations, okay? So we've got the summation of minus 2 times yi. So I'm going to bring the minus 2 outside of the summation. Okay, anything with yi or xi involved has to stay to the right of the summation symbol. Anything else is a multiplier and can come outside. Then I've got minus 2 times minus a, so that's plus 2a. And because nothing there has xi or yi involved, I can just have the sum of 1. So 2a times the summation of 1. And then we've got minus 2 times minus bxi. Now the b and the minus 2, well sorry, the 2 and the b rather, can both come outside, but the xi has to remain on the right hand side of the summation. So plus 2b times the sum of xi. Now, because I'm trying to minimize this, the minimum will occur when the derivative is 0. Okay, so essentially minimum occurs when ds by dA is equal to 0. So I need to put this equal to 0. And what I'm going to do is, putting it equal to 0, I want to get a equals. That is where I want to go with this. So I'm going to keep that on one side, so 2a. So I'm going to rearrange it at the same time, summation of 1. I'm going to add that to both sides, so 2 sum yi, and I'm going to take that from both sides, take away 2b summation of xi. Now, I can divide through by 2 at this point as well, so let's just do that. Divide through by 2. There we are. Okay. Now, the sum of 1 from I is 1 to n is 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times. So how much is that? Well, the sum of 1 has got to be equal to n. So the sum of 1 is n. Okay, so I've done a few little simplifications there, and now I can divide through by n, so that a is equal to the sum of yi over n, take away b times the sum, oh, whoops, I wrote a square root symbol there, times the sum of xi over n. Okay? But what are these? What is the sum of yi over n? Well, that's just y bar. That's the mean of y, because it's adding up all the y values and dividing by n. And adding up all the x values and divided by n is x bar. So actually this is a is equal to y bar, take away b, x bar. So if you rearrange that, you can see that y bar has got to be a plus b x bar. So remember, our regression line was y equals a plus bx. And what that's telling you is that the regression line must go through x bar y bar. X bar y bar satisfies the equation. So we now know from that that the regression line has to go through the point x bar y bar. Okay, so that's one success already from this. Right, so now that we've got that, the next thing is I now need to differentiate S with respect to B. So I'm hoping, fingers crossed, I've got enough space for this. Let's see, shall we? So ds by db Okay, so I'm now going to differentiate this with respect to b. So b is now the variable. All the other things, yi, a, and the xi, these are all constants. So the derivative, so using the chain rule, okay, the derivative of the inside is, so we're going to have minus bxi there, aren't we? So the derivative of the inside is minus xi. And the 2 is going to come down to the front. So minus 2xi. And then we've got yi, take away a plus bxi, and I've dropped 1 from the power. Okay. Now I want to do what I did here. I want to expand out all the summations. Okay? So, what have we got? We've got minus 2 xi yi there. So the minus 2 can come outside of the summation, but the xi yi have got to stay where they are. Then we've got minus 2xi times minus a. So we're going to get plus 2a times the summation of xi. And then we've got the minus 2xi times minus bxi. So that's going to get us plus 2b, and I'm going to have the summation of xi squared. Okay, so that's where we're at. Now, what I'm going to do next is I'm going to have to now consider that the minimum occurs when ds by db is equal to 0. Okay? So, I'm going to put this equal to 0, and I want to get b equals. That's my target. So I'm going to write that as 2b times the sum of xi squared is equal to 2 times the sum of xi yi, so I've moved that over to the other side, and then take away 2a times the sum of xi. Right. Okay. Now, clearly the 2's can go. Bye-bye. Divide through by 2. Now, the a I worked out here. Okay, so I know what a has to be. So I can substitute this in for a. So I'm just going to leave the left-hand side the same. So b times the sum of the xi squareds is equal to the sum of xi yi, like that. Take away, now the a, I'm going to have the sum of yi over n, take away b times the sum of xi over n times the sum of xi. Now, this isn't looking too pretty, but let's simplify this. Now, I've got to do a few steps in one because I'm going to run out of space otherwise. I still want to get b equals. Now, the problem is that I've now got b on both sides of the equation. So, b times the sum of xi squared can stay precisely where it is. I've got the sum of xi yi there. Okay, so let's leave that where it is. Actually, I've changed my mind. It's all part of the process. Right. Let's multiply it out and move the b onto the other side. We've got minus, minus, so plus b times that times that. So I'm going to add that, sorry, subtract that from both sides. So take away b times, we've got the sum of xi times the sum of xi. So that's the sum of xi all squared divided by n. Okay, so that's on the left-hand side. And of course I could factorise that, couldn't I? Factor the b out, like so. And what I've got left on the right-hand side is I've got the sum of xi yi take away the sum of yi over n times the sum of xi. So that's the sum of xi times the sum of yi over n. So then I can divide both sides by this bracket. And what I'm going to be left with is b is the sum of xi yi take away the sum of xi times the sum of yi over n divided by the sum of xi squared take away the sum of xi all squared over n. Now if you remember back to the previous section, that is Sxy and that is Sxx. Okay, and so that is how we can derive the regression line of y on x. Okay, so this is my regression line. Y bar is equal to a plus b x bar. Okay, that's the line that I'm working with. And the b, the gradient, is this. Okay, so I can use that to work out a. Calculate the value of b, substitute it in there with your x bar and y bar, and that allows you to work out the value of a. Okay, and so that is how the least squares regression line for y on x is derived.